Ok, donc Monsieur Yonghui XU, on est là, on a le plaisir aujourd'hui de vous écouter pour votre soutenance de thèse. Donc je vous présente le jury, donc Arnaud de Coviac, moi-même, professeur à Sorbonne Université. Le jury est donc composé des rapporteurs Pierre Branchet, professeur à l'IMFT Toulouse, enfin Paul Sabatier, Toulouse 3, je ne sais plus ce qu'il faut dire. Stéphane Lodizès, chercheur à Aix-Marseille à l'IRFE. Ensuite, nous avons Vincent Brion, qui est ingénieur de recherche à l'ONERA Meudon. Et puis ensuite, les encadrants, Maurice Rossi, chercheur à Sorbonne Université, Daniel Fuster, chercheur à Sorbonne Université, Yvan Delmont, enseignant-chercheur à Sorbonne Université. Voilà, donc on vous écoute pour une 50aine de minutes, okay. Puis ensuite on passera à la séance de questions.
Ok. Merci le président de jury et merci à tout l'ensemble de comité. Merci d'être tous venus ici. Je suis Yonghui, je fais ma thèse à l'Institut Jean-Leron de D'Alembert ici pendant les 3 dernières années avec mes encadrants Maurice Rosé, Yvan Delmont et Daniel Fuster. Maintenant, please let me switch to English. I will talk about my thesis on numerical studies on vortex dynamics for helical vortices and two-phase vortices. The motivation of this thesis is going to better understanding the dynamics behind a rotor system. As you can find here, the flow behind a wind turbine, or the flow just below a helicopter propeller, or a rotor system submarine for a boat. The subject is mainly divided into 2 parts. The first part concentrates on monophase helical vortices, which correspond to the first 2 images here, and the second part is a two-phase vortex, similar to the image 3, but in a toroidal shape, which means a ring shape. We're starting by talking about monophase helical vortices. You can find here a more clear structure for the flow behind a wind turbine in a wind tunnel test, where the vorticity is visualized by smokes. We assume we are focusing on the part just in the near range behind the blades, and the structure is similar to the illustration here. At first, it's periodic along z direction with length 2 pi L, which we called helical pitch in a cylindrical coordinates, and L is the reduced pitch. In the same way, we assume the base flow here is helically symmetric, which means if we're rotating the flow for a certain angle, for example, theta s, and translating it in z direction for a proper distance, for example, h here, the flow remains unaffected, which means, for example, the 2 points A, B in the same helical line have a same variable we call vis-à-vis equals a constant. You can find here, since if in the assumption of helical symmetry, the 3D flow can be is reduced to a 2D configuration with only 2 variables r and vis-à-vis. We use 2 plans here. The first is called plan P0, as you can find here in a z theta plan. It's a horizontal plan and perpendicular to the z direction. And another plan, which we call the pi perpendicular, is perpendicular to the direction of axis. We call it as blue here. The A is the center of vortex filaments or vortex, and RA is the distance between the z-axis and the point which we call the helical radius. In the same way, we introduce a new orthogonal basis locally in this plan with AB as the direction of axis, and R is usual and phi is a third component. The parameter alpha here is a normalization parameter. So we starting by study the base flow. As you can find here is one experiment done by Gahanda at ICFE, where the inlet flow is coming from left side. Here is a two blades rotor, and the 2 dies are injecting with each attached to the end tip of the blades. We can clearly find behind the rotor is a helical structure. Here is another experiment done also by Gahanda, where in this case the die is put just a little bit below the propeller in a fixed point, which allows us to see the particle motions inside. We find in this case, at first it contains azimuthal rotation around each helical line. And on the other hand, we can see the actual flow is presenting along the center of vortex, as you can see with the green traces here. And we can find the velocity in the middle is way much larger than those far away, and we call this local helical motion within the core as a swirl. We are focusing on this point because swirl is very important for the stability analysis, which we will show you later. So we're starting by looking for a like solution. We both know it's known that for a 2D flow, we have this as a solution, where the omega z and the uc here is actual velocity and the vorticity and the velocity. The v function is a stream function. If we extend the flow to an axisymmetric flow, for example, a ring shape, in the same way, in direction theta, we also have a similar solution, which is very early studied by Bachelor. In this case, it's stationary because we see the actual velocity and the vorticity is a constant around if the stream function psi is a constant. In the same way, we're looking for the solution for helicophoresis. The solution can be written in such a form. We use direct numerical simulation to solve the problems. We write in the dynamic equation and the vorticity equation in such a form with two new parameters, where the UH is related to the actual velocity, and the bar omega is related to actual vorticity and the velocity. The G function is defined as below. With some mathematical calculation, we can obtain a relation between the vorticity, velocity, and the stream function. With this, where L here is a linear operator. This function is used in the code called hélices, where it allows to generate and simulate the helical symmetric vorticities with swirl. It's built like 10 years ago, and we just introduced these new functions inside. So, as we know, the helical motion is usually rotating, and we cannot say it's stationary. What we do is we attach our reference to the hélice, like the one showed here, and we call this frame as a translating frame. In the same way, we're looking for other solution, and we're neglecting the viscosity term. It's stationary, so the term dependent on time is 0, which left us these two conditions for the stationary, and which means for a helically stationary flow, it must exist two functions, where the UH and the bar omega is a uniform function of stream function psi. Here is what we do. We propose initially a Bachelor vortex in the pi perpendicular. Like you can see here, it's not a stationary solution. We left it evolving with time, as we just use it as an initial condition, and we hope after some time it can lead us to the visquous quasi-équilibre states. One example you can find here, at first we project the axisymmetric flow into a pi0 plane, where in the case with L equals 0,3, it turns into a banana shape. Here is the center of vortex, which allows us to manipulate the position of vortex. We then simulating the flow evolution in the p0 plane after t equals 20, where it's reached its equilibrium. This is a final form, which is almost around here. We can see in the p0 plane it's very difficult to distinguish the difference, so we project it back to the p perpendicular plane for analysis. You can clearly find the flow evolutions here. At the beginning, it generates some filaments because it's not a stationary solution. Then the filaments is diffused due to the viscosity, and slowly it tends to the final solution. We verify the flow has reached its equilibrium with the two uniform functions that we mentioned before. Here are two examples with different L and different cos and different actual velocity. A more convincing evidence is that since the bar omega is a result as a difference of the black part and the green part here, for the first case, the blue part is almost 0. It's not so convincing, but for the second case, these are at the same order, and we can clear the difference between two did give us back a uniform function, which is very convincing that we have reached its equilibrium. Here is two examples of different base states with L equals 0,3 and L equals 0,7. This is a view at P0 plane. This is a view at a perpendicular plane, where it's scaled with the cosines, which is R here. We use 5 parameters to characterize our base states. R here is a stagnation point here. we have the reduced pitch, which is fixed by the simulation, the circulation, which is invariant over time, RA, which is helical radius here, A is the call size as a dashed circle here, and the WB, which is actual flow of amplitude. These three parameters are dependent on time. So for the final states, from the original axisymmetric shape, it's deformed with mainly two parts. The first way is we called MD equals 1, which is a curvature mode. It shifts the vorticity. Here is to the left side, and the second part is MD mod MD equals 2, where it's due to the Gaussian string and the curvature, it deforms the shape of vortices from a cylinder to an elliptic. These are the source of the instability. You can find more details in articles that we published earlier this year, where we describe the details how we use an iterative procedure to obtain a specific base states, where the gamma is chosen to be 1, RE is helical radius is 1, L is as we defined, and the specific call size and actual strength as we wanted. We then pass to study the instability of helicophoresis based on these base states. The theory has very early studied for string vortex, where by Tingon and Mohan and Softman, we can freeze for a flow defined as for perturbation defined in such a shape. We have a resonance between two Kelvin modes on a straight vortex, where it has the same wavelength, the same growth rate, and the difference of the Kelvin modes here equals the modes of the deformation for the base states. For example, MD here can be either 1 or 2, as we discussed above. The instability can be mainly divided into two types. The first is long wave instability, where the perturbation length is of the size of helical pitch. Here, it's only a displacement, as you can find one experiment result by Domalivec here. It shifts each turn of filaments. Source on below is nonlinear evolution, is no longer a linear stage. And for the short wave length, the second type is short wave length, where the perturbation wavelength is of the size of call size. Instead of displace the helical turn, it modifies the core structure based on the difference of the resonant mode. If it equals 2, we call it elliptical type, as you can find here. It's also an experiment done by Domalivec, and if it equals 1, we call it a curvature type. This mode is very difficult to capture, so until now there's no clear experimental observation. Here is how we obtain the mode. We use another code called Eliga-Zedlin, where for a base state that we want, we add a white noise superposed on the base states with a very small amplitude, and we then left it evolving with time. As you can find the real simulation here, at t equals 0, we add the perturbation. The unstable mode is growing with time, and after a certain time, only the most dominant mode, which has the largest growth rate, appears. This is the dominant we are looking for. For all the simulations that I will introduce below, we use Reynolds number equals 10 times 4. We use a different scaling law here because the theory is done with the call size, but in our simulation, we are rather use the helical radius. So first is a long wave instability mode that we obtained. As you can find on the left side is perturbation mode we found, which is similar to the one found by one of the previous PhD students, Jan Saleswick, during his thesis in our group. We find the same structure for the long wave mode, where clearly we find it's just displace the helical vortex. And here are our results. On the y-axis is the dimensionless growth rate, and on the x-axis is a dimensionless wave number. The black curve here is a theory done by Gahanda with the following equation. On the left image, we keep L equals 0.3. We use a very weak actual velocity, but we vary the cos s from 0.08 to 0.15. We can see if we increase the cos size, it tends to stabilize the long wave instability, which is reasonable because the theory is done for helical filaments, and as long if the cos is too large, the theory is no longer valid. But on the right side is we keep the cos s relatively small, and we vary the actual velocity. We can find in this with our simulation results, the actual velocity does not have a huge impact on the long wave modes. We now pass to the elliptic short wave instability. Here is how we analyze it. You can find one of the dominance mode we found during our simulation. Here is this view at P0 plane. It's a zoom view of the vorticity. It's very complex, so we project it to the P perpendicular plane. And we extract its normal modes. You can find here the clear structure of the undominant mode. For the dominant modes, for this mode, we can decompose it into different modes. You can find in the figure here the energy ratio of each mode, and clearly we find the dominant modes here is m equals -2 and 0. In the same way, it's their radial distribution. We then name the modes following the methods used by in lab Yonghui, where MB is the dominance mode equals -2 and 0. LB is the name of the label of each mode, which you can easily be understood by with how much bracket we have for the radial distribution. And for modes m equals 0, we have 1, 2. And for modes m equals -2, we have just 1. So we name this mode -2, 0, 1, 2. Due to different naming method, this mode is similar to the modes we called in the article named 0, 2, 2, 1. It's just the reverse of the sign of the dominance modes. So the theory for the short wave instability is done very early by Lagasse at 2007 for a straight vortex, whereas just for remind the difference of the dominance mode equals 2. In this figure on the y-axis, we have the dimensionless wavelength. On the x-axis is the strength of actual velocity, and the dark and the white part indicate the strength of unstable modes. If it's darker, it means it has a higher growth rate. This mode, as predicted, is depend very much on the core actual velocity W0. As you can understood by different slicing of the unstable modes here for different actual velocity. In the same way, Blanco-Rodriguez has extended the theory for a helical vortex, but they neglecting the effect of torsion in their theory. Here is the structure of the three modes that we are interested. For the modes -1, 0, 1, 1, -2, 0, 2, 2, and -2, 0, 1, 1, 1. With our simulation, since we use direct numerical simulations, the torsion effects is not neglecting, which is a huge difference between the theory and ours. So here is a 3D structure of the three most unstable modes that we obtained. You can find here is its structure 3D, and in the middle is the zoom view of the small cube here. The red and the blue parts means positive and negative vorticity, with the surface is the isosurface of the vorticity at plus and -0.3 of its maximum in the center. We can find the structure here is very complex, and it did modify the structure of helical vortex. That is the most important thing for short wave instability. Here is an example for the modes -2, 0, 2, 2. It's their structure in the P perpendicular plane. The dominant mode is -2 and 0 as we are looking for, and the difference is 1, 2, and 1, 2, that's why we call it -2, 0, 2, 2. On the other hand, we just did another simulation with reverse actual velocity. For helical motion, if it's positive, it means it's going to this direction, but if it's negative, it's going to an opposite direction. You can find two theory correspond to different direction here also by Blanco with some corrections we have added, and those are our simulation results. We can find in both ways the unstable range fits quite well with the theory and also with the growth rate, but it still has a very little differences. And also for the frequency, we obtain a quite good value. So we are curious about the difference, and I will explain more detail with the example of curvature instability here. The difference of the curvature modes and the elliptical modes is the difference of dominance modes become 1. And this mode is very sensible, and as discussed by Blanco the gas, is always dominant by elliptical modes with W0 equals 0. It can be dominant when the cosine is very small. That's why experimentally it's very difficult to capture these modes, but numerically we can isolate these modes with a specific value of k. Here is the original expression by Blanco with black with all the things black part here. And it corresponds to the black curve here, which corresponds to the case of zero torsion. We add 2 correction terms here in red, which, as you can see, so as an effect of torsion, which you can see just shift the unstable range to the right side. And it's dependent on different pitch. So this is all we found. We did a global scan for the base states L equals 0.7, R equals 0.15, and the actual velocity equals 0.2. These are 3 modes we have found, and these are 3D structures corresponding. Compared to the elliptical shape, we didn't find these modes have a more complex structure. Also, these 3 modes are also predicted by the theory by Blanco the gas. If we focusing on the first case, we started by studying the effect of actual velocity. This is the structure of this mode in P0 plane. Its dominance mode -1, 0, and the bracket, which equals 1 and 3. So we starting by study the effect of jet stress. Here's the original profile with W0 equals 0.2. We change nothing, but add the actual velocity to 0.27. We find the modes 1 to 1, 4 seems stable and shift a little bit. The modes 1, 3 didn't change too much. We then still increase the actual velocity to 0.32. We find that the modes 1, 4 is disappeared. 1, 3 in the same way is just slightly changed, and the mode 1, 2 is appeared. We then compared our results to the theory of Blanco the gas. They only giving the theory prediction for 2 specific actual velocity amplitude with 0.2 and 0.4. They don't have the theory for the things in middle, but we can find the mode 1, 4 is disappeared if we increase actual velocity, and the mode 1, 2 is appeared if we increase actual velocity, and the modes 1, 3 didn't change too much. So our numerical simulation results fits quite well with the theory, but we still find some difference here. So is this really an effect of torsion? We pass to the modes -1, 0, 2, 4 here for the same base states. So here you can also find its structure in perpendicular plane. The dominance mode -1, 0, and the bracket 2, 1, 2, 3, 4 as theory. This is some numerical results we have obtained. The red and purple curve are the theory prediction with the correction terms that we added, and the dashed line is our numerical results. We can find in both cases the unstable range fits quite well with the theory, but we have a little bit difference on the growth rate. The frequency is also not bad. We also did on the right side here is with base states with negative actual velocity is a minus sign here, and on the left side is a case with positive actual velocity. We also did many other simulations with different reduced pitch, but we keep the variable y epsilon, which stands equals 0, 1. We can see we reduce the L from 0.6 to 0.04. We can see for the negative case, it seems works a little bit better, but for the positive case, we find the growth rate is just the theory cannot well predict the behavior of DNS results. That's why we can conclude there indeed exists an effect of torsion, and the theory, since it's done for the case with weak torsion, also torsion can be neglecting. We should improve. We should change the parameters for the theory. We cannot just apply it as we want. So as a conclusion, for the monophasic part, we have generated the base states for the helicophoresis with swirl, with new criterion for the inviscid steady states, and we use a iterative procedure to obtain a base states as we want with a very good precision, which is very important because the actual velocity is very sensitive for the shortwave instability. We successfully obtained the elliptical modes and the curvature modes with our DNS code, and we show the effect of torsion does exist for helicophoresis. Now we pass from the single phase case to the two phase case. This part is inspired by some interesting videos that we have found online. As you can see here, a dolphin is generating a bubble ring. A similar type of structure of bubble can be generated also by a scuba diver, as you can see below. The bubble ring can remain its shape for quite a long time without breaking into smaller bubble, which is a classical bladder instability that we hope to see. We are curious. We study its dynamics on 3 parts. The first, how the bubble ring is generated. The second, what is the evolution afterwards, and the third, why it can remain stable. We use the code basilisk, which is developed in our code to run the simulation. We assume the dynamics is simply axisymmetric. We use a nozzle to stand the blowhole of bubble. As you can find just the type of structure here. We put the gas initially inside the nozzle in a water environment. We then push the gas outside, and ideally to form a tornado shape afterwards. This is a plan of simulation. You can find a more detailed structure here. The white part is a wall of nozzle. Yeah, we have used a sharp cone here to simplify its detachment. The red part is a bubble, and the blue part is water. The nozzle has an inner wall with radius R0. We use 3 parameters to control the simulation. The first is Reynolds number. We choose it equals 5,000 to a value close to the real world. We also use the Weber's number, which is defined here, and the RB, which is the ratio of the thickness of bubble and the inner radius of wall. We use this parameter to control the volume of bubble. These 2 values is varied for our simulation. For the inlet velocity, we propose it has an amplitude U0. Along with R0, we use these values for the adimensional. The flow is smoothed by 2 arrow functions on time and on radial distance. With Earth here is the arrow function. Delta here is the thickness of initial vorticity layer because the velocity of fluid is 0 at the wall, and it's U0 in the middle. We just generate a very thin layer here near the wall of nozzle. Here are 2 simulation results, as you can find here for the first case, where on the top half is a phase field, blue is water, red is air, and on the bottom half is a vorticity field. We can see in first case, tornado shape bubble is indeed generated. We can assume by here as an axisymmetric shape. But in the second case, we only obtain a spherical-like bubble, which is in the middle. So we'll take a look at the simulation. The bubble is ejected out with typical vorticity roll-up is generating near the wall of nozzle. It then break up the bubble in the middle with some complex actual interface vorticity at the interface of bubble. It is then every mechanism is interacting with each other and being quite complex. So for the generation phase, we assume there is two forces competing here. The first is vorticity roll-up, which break up the bubble from the middle. The second is capillary force, which want to drag the bubble back to center. We assume two parameters are important, as Weber's number indicates the ratio between the inertial energy and the surface energy. And also for the RB, which controls the volume of bubble, and it can modify the surface tension by changing the radius for different volume. For the simulation with Weber's number equals 3, we can find for the first case with RB small with equals 0.6, we just obtain a spherical-like bubble. If we increase the bubble size to 2.4, we can see initially a toroidal-shaped bubble is formed, but is rapidly dragged back to center due to the surface tension. We see in this case, the surface tension is much stronger than the inertial. If we increase the Weber's number to 20, we can find for the case with small bubble volume, we find a similar dynamics, but for RB equals 2.4, we successfully obtain a toroidal bubble. We see in this case, the surface tension is almost the same order as the inertial. Then, if we increase the Weber's number to 100, we can find in both cases for a small bubble and a large bubble, we have obtained a toroidal-shaped bubble. In this case, the surface tension is just too weak compared to inertial. So as a conclusion for the generating part, we think the generation contains mainly three mechanisms. The first is a standard vorticity sheet roll-up. The second is a capillary wave generating at the interface of bubble, and the third is a breakup of bubble. And the toroidal shape is always preferentially formed when we increase the Weber's number and the bubble size. The typical value for scuba diver is around Weber's number equals 20 and RV equals 4, which is valid, is in a good agreement with our DNS results. We then focus on its dynamics afterwards. As you can see in the video here, a bubble ring is rising in a water tank 40 meters underwater. We can find the radius of a ring is enlarged, which is not so evident here. We assume the dynamics happening here is something similar to a stretching mechanism. We use 4 parameters to characterize our DNS results. So with the swirl number, which equals the ratio between the rotating speed around this bubble and the capillary velocity. Here the gamma is the total circulation around the bubble, and RB is the core size of bubble. During the simulation, we found over the time it has an increment for the swirl parameter QS, then it tends to a constant. During the increment phase, since the circulation is almost a constant, we must have a decreasement of bubble radius RB, which is a consequence of the increment of bubble ring as to illustration here. The ring become larger and the volume is conserved, so the section of bubble becomes smaller and indicate a smaller core radius. And we should remember in the same time, the source motion is being stressed here. If we take a look at this vorticity distribution around here, we can find it's still very complex with a very large vorticity concentrated near the interface, which is still, this flow is still very complex for the stability analysis. Since we can write in the vorticity equation in such a form where the omega tilde means is the autosimilar solution for vorticity after stretching, which gamma is the stretching parameter, we can move our model from a toroidal bubble to a tube bubble. We then duplicate our vorticity field to a 2D simulation. It's no longer axisymmetric, it's a pure 2D plane with basilisk. We can find over time the shape of the bubble become round. The vorticity inside is become way much smoother with a thin layer just generated outside the bubble. We assume after the stretching mechanism, this is how the base flow acts for a bubble ring. So we use idealized base states for our stability analysis. We propose simply inside the gas phase, is a pure solid rotation, while outside the bubble phase, the vorticity decays rapidly with time with distance delta. We use two new parameters with different scaling law here. And for our numerical results, we find the Q is increased to a value close to 1. Here is a stability analysis with a two-phase code in-house that was made by us. The blue curve here is original Plato instability. And we can find with the increasement of swirl strength Q, the Plato instability is being stabilized until it passes some value around 0.03. So it becomes totally stable, which means the swirl can stabilize the interface Plato instability. You can find here a portrait fish is trapped by the vortex string, which just exactly show how strong the rotating speed is around the bubble. So, sorry. So as a conclusion, the dynamics for the bubble ring can be mainly separated into three parts. The first part is the formation of a bubble ring, where it contains the vorticity roll-up, it contains the capillary wave generation at the interface, and the breakup of bubble. And after the generation is being stretched, with the increasement of ring radius. In the meantime, the swirl is being stressed, and the vorticity profile is being way much smoothed inside with the thin layer just outside. With this kind of base states and a strong swirl, the Plato instability is being stabilized. That's why we can find this bubble can remain stable for a very long time. So in the future, there are still many things can be done. The first is, as you can see, the effect of torsion is not very good explained. So there are many theory and numerical part can be done with this part. And on the other hand, our results will go to a collaboration with Yonghui from Japan, where we want to see the nonlinear development for shortwave instability and the interaction between the shortwave and the longwave modes. Similar to one experiment, the results done by Gahonda. As you can see here, the interaction of the two modes. For the two-phase flow, in the same way, we just studied the case for a toroidal vortex. We can extend the study to a helical vortex but in a helical vortex, but a two-phase configuration similar to those flow just behind the rotor of a boat. In the same, where based on adding all the things for the monocase phase, there is another impact from the interface or the surface tension. And that's all of my presentation. Thank you for your listening.
Okay, thank you. Merci. You were fast.
Okay.
Ok. La salle se stabilise un peu. Et je pense